Welcome to section 3.1 of the Data Management textbook. This chapter deals with linear correlations and scatterplots. Let's begin. The first vocabulary word will be the dependent or the response variable. This is the variable that is affected by another variable. Next, we have the independent or the explanatory variable. This is the variable that causes changes in the other variable. Next is linear correlation. The linear correlation is the relationship between the x and y variable. And this can be inverse or direct. I also have a photo here that would help explain it. So as this picture shows, linear correlation can be negative or positive, and positive means direct, negative means inverse. For example, a direct correlation would mean as x increases, y would also increase, whereas a negative linear correlation would mean as x increases, y decreases. The linear correlation can only range from -1 to 1, with every number in between being part of the correlation coefficient. As you can see, the picture has classified as a range of strong, moderate, and weak. The next vocabulary word is the scatterplot. A scatterplot is a graph that plots the data as individual points with regards to the x and y variables. The next vocabulary word is the line of best fit. The line of best fit is an imaginary line that you can draw in between the points on a scatterplot. This will give you an approximation of where the mean points will be. Next is covariance. The covariance is a formula which helps you derive the mean of the products of the deviations of two variables. And finally, we have the correlation coefficient, which is noted as R. This formula gives you a quantitative measure of the strength of the relationship between two variables. Statistical studies often find linear correlations between two variables. The independent variable x is usually plotted on the horizontal axis, and the dependent variable y is usually on the vertical axis. Two variables will have a linear correlation if changes in one variable tend to be proportional to changes in the other. For example, linear correlations can be positive or negative and can vary in strength from 0 to perfect. The correlation coefficient is a quantitative measure of the correlation between two variables. Negative values indicate negative correlations, while positive values indicate positive correlations. The greater the absolute value of R, the stronger the linear correlation, with 0 indicating no correlation at all, and 1 or -1 indicating a perfect correlation. Manual calculations of correlation coefficients can be tedious, but perhaps you could use a graphing calculator to help you solve it. Now we move on to the formulas. So as I said before, we have two formulas, which are the covariance and the correlation coefficient formulas. The covariance formulas were first used by mathematicians in order to find, as I said in the definitions, the mean of the products of the deviations of two variables. We do, however, use the correlation coefficient, otherwise known as Pearson's R, or as Pearson's product moment coefficient of correlation. This formula started off as R equals the standard deviation of xy over the standard deviation of x times the standard deviation of y. Afterwards, Pearson used algebraic manipulation and the fact that the sum of x equals the number of terms times the average of the sample space, and he rearranged it to make this formula. Now we move on to example 1. Classify the relationship between the variables x and y for the data in the following diagrams. As we can see in A, as x increases, y also increases. Therefore, it has a strong positive correlation. As you can see in B, as x increases, y decreases. Therefore, there is a strong but negative correlation. In C, the data is very spread and has no distinctive trend. Therefore, there is 0 correlation. In D, the trend seems to be moving upward, and as x increases, y also increases. Therefore, since the data is still a bit spread, it is a moderate to strong positive correlation. In E, we can see that the trend is still moving upwards. However, the data is more spread than in D. Therefore, the correlation is weak to moderate and positive. Finally, in F, we can see that the trend is that as x increases, y decreases, and the data is still spread. However, the data is more grouped than in questions D and E. Therefore, it is a moderate to strong negative correlation. Example 2. A group of data students want to know if the amount of coffee their teacher drinks affects the number of questions that he assigns for homework each day. The data is shown in the following table. A. Make a scatterplot of the data. Does there seem to be a correlation between the variables? And B. Calculate the correlation coefficient. So I've already made the scatterplot. And in B, you have to first make this table because it gives you all the data you need to sub into the equation. This is the equation. And the answer is R equals negative 0.989236. Therefore, there's a strong negative correlation between the amount of coffee and the homework that he gives.